Good afternoon, this is Schweitzer, and let's look at a little bit of worksheet on kinematics of vertical motion. Of course, we know we've a little bit about the mathematics already, and we're going to be graphing this out a little more. But rocket fires engines to launch straight up from rest with an upward acceleration of 5 meters per second squared for 10 seconds. After this time, the engine shuts off and the rocket freely falls straight down back to Earth. And a 10-second burn would actually be a pretty long burn. I mean, even large rockets, burn might only be 2 or 3 seconds, and that's it. But either way, so sketch the 5 meters per second for 10 seconds. So at this point, what's my acceleration? Well, the acceleration is constant at 5 meters per second. So let's grab ourselves just a straight line. Use a pen. Here's our 5, and it's just going to be like that. Okay, going to cut across here for 10 seconds, and then it changes. The engine shuts off. Okay, so one little side question is what is the acceleration after 10 seconds? Okay. And the answer to that is that now you're just in Earth's pull, and that would be acceleration of gravity, which is negative 9.8. So if you had to graph that, you would like draw it down, and then you'd need to go negative down to the negative 9 point. I don't allow room here, but you would cut across at that point like that. All right. Okay. Sketch a graph of the velocity as a function of time, t0 to 210. Okay, so velocity. So every second it gains 5 meters per second. So sometimes we could just do a little table here, and 1, and so let's say time, and then velocity. So 0 would be 0, and then 1 would be 5, and 2 would be 10, and 3 would be 15. I essentially am running a linear relationship here of the velocity times t equals velocity initial plus at. So let's take our grid here and graph it. 1 would be 2 seconds would be 10. 4 seconds would be 20. 20. There we go. And 6 seconds would be 30, and it would just look something like that, and it's going to just continue up. A little sloppier there, but that's it. Okay, it says from the graph drawn in part B, determine the velocity of the rocket after initial 10 seconds. So from the graph in part B, determine the velocity of the rocket after the initial 10 seconds. All right, so that's just going to be right here. So 0 plus, I could use 10 if you wanted, negative 10. All right. Second. Yeah. So 5 times 10 should just be 50. Okay. Meters per second. 50 meters per second. All right, and that just goes right here. From the graph drawn in part B, determine the height of the rocket after 10 seconds. All right, so now this is velocity divided by time. They want you to use the graph. Okay, so we know that the area under the curve is going to be the distance traveled. So I got the 1/2 of the length times width of that square, giving us our triangle. The length is 10, and the velocity at the 10-second mark was 50. Should probably be right there, would be the best, most accurate line, times 50. So 10 times 50 is 500. Cut that in half, and we get 250 meters tall. Okay, next one. We have, all right, make a claim about the numerical value of the acceleration of the rocket 10.1 seconds after firing when the rocket engines have completely shut off. Okay, so it's the first time I've seen this page, and so the acceleration of the rocket number 1 we just talked about earlier. Shuts off. Now our Earth it's negative 9.8 meters per second squared. All right, flipping it over. All right, use the definition of free fall to explain your reasoning to part E. Okay, so essentially, I would say free fall would be essentially we're just being pulled by gravity. So gravity is what we have here, and gravity pulls everything at the same rate, which is acceleration equaling 9.8, and that's it. Now we're still going to have a positive velocity, all right? We're still going up, positive velocity. Just not the acceleration goes from equaling 5 for this first part to now, after this point, negative 9.8, which just means that your velocity is going to start to dip. It's at 50, it's going to start working its way down to 0 before it peaks and then starts its way back down. So 10.1 seconds after the rocket was launched indicate whether the rocket is moving upward or downward. Okay. Still going up. Choose one piece of evidence to support your claim. Well, the best one here might be the positive 50 velocity. All right. That is what's causing you to go up. You're going up at that velocity. Going up. And the acceleration is not quite enough. Acceleration of negative 9.8, or you might say even negative 10. And at that point, every second we lose one, it's going to take 5 seconds for it to reach the ground. Okay. And I noticed that the original acceleration was 5, so it must have taken twice as long to get up there because it half the acceleration. 10, 5 versus the 10. So, anyways, that looks pretty good.